Okay, so a reverse exponential, therefore, we can now check whether this satisfies our condition. And the answer is not, because if I go back, this is the VP that is allowed, right? Maximum 1.0417, and the N, the minimum is 1. So if I want to maintain, because the feeder, if you can remember, right, the feeder of the graph, this is a feeder and this is a VP. So essentially all these are from the same node. Same node. So it means that if the minimum VP is 1, the end of the feeder, it should be 1 as well. Minimum, right? At the minimum, it should be 1. So 1 is here. And this is less than 1, obviously. And therefore, this does not satisfy the condition. And we need to perform voltage regulation. And this is how we justify whether voltage regulation is allowable or not. And to be more conservative, remember the bandwidth of 0.0083 per unit. We can add on to this one so that we can get the minimum value that is higher to get a more conservative analysis. Okay, so next one. So here we try to perform voltage regulation. So now instead of S1 at equals to 0, we move the regulation, okay, the regulator to S1, to a location at S1. And this location at S1 is 1.75 meter down the feeder, right? Just now it was 0, now it's 1.75 down the feeder. Again, they ask, what is the specified best R and X setting? So it is also to mention to you that, so in this example, right, I'm moving the regulator down the feeder, but I'm still not performing any active regulation, okay? So the regulator just move from S equals to 0 to S equals to 1.75 and see what is the effect. So I set the R and X setting to be 0. So I'm not using the regulator to manipulate what is the voltage that is coming out from the regulator. So R and X setting equals 0 in this case, right? So it meaning that the regulating point is still at the locations of the regulator. So compare the case 1, case 2. In case 1, S is located at 0, and the regulating point is located at the voltage regulator location. In case number 2, the voltage regulation moved to 1.75 meter down the feeder, and the regulating point is also at the locations of the voltage regulator. All right, so you can compare the two conditions here. So it's also, I think by now you can guess that the voltage, the R and X setting of the voltage regulator is for us to manipulate what is the output voltage of the regulator. So in these two cases, when the regulating point is located at the locations of the voltage regulator, R and X setting is essentially 0. And we are not doing any manipulation towards the output voltage of the regulator. But this affects the analysis because the regulator has moved 1.75 meter down the feeder. So with that, right, we have to consider this thing, okay? This thing. This is the formula for us to calculate what is the voltage drop when entering the regulator. But there are some logic to it, right? So now the regulator is 1.75 meter down the feeder. So in that 10 meter of the feeder, the total load is 4,000 kVA. But at 1.75 meter, the loading of the feeder is less than 4,000. It's not 4,000, right? So it's proportional. The load on the feeder is proportional to the length of the feeder. So in 10 meter, you have 4,000 kVA. In 1.75 meter, then you can calculate what is the loading, or what is the load on the feeder in 1.75 meter. So this as adjusted ADJ for adjust. So as adjusted as a function of L means that the as adjusted value should be the value of the S reflecting the length of the feeder. So in 10 meter, you have 4,000, 1.75 meter, you have how many?